So, today we will perform experiment on series LCR circuit. So, series LCR circuit you can see here. So, this R, resistance R, inductance L and capacitance C. So, they are connected in a series with this power supply. This is basically AC power supply. Okay. So, from here this current you will get in this circuit, because this voltage is this basically AC voltage. So, current you will get of same frequency. This current will vary in this circuit, this IT equal to I0 sin omega t, right. So, what we will study in this experiment is basically the variation of current and voltage in this LCR series LCR circuit, as well as this circuit is basically it called this tuning circuit. So, this circuit is used to tune tune of what? So, basically if you just vary the frequency, this current you can maximize the current in this circuit. Okay. So, that is why in earlier days in radio, really this to increase the volume or to just find out the channel. So, this whatever this we varied. So, that is a we vary the basically frequency. Okay. For a particular frequency, then when it matches with the signal frequency, then there will be resonance, and for that maximum current flows in the circuit, means you will get the strong signal. Okay. So, here if current flows in this circuit, then you can, what we can do, we can measure the voltage across the resistance. So, this VR, we can measure the voltage across this inductor. So, that is VL, and we can measure the voltage across the capacitor. So, that is VC, and you can basically, if you plot this voltage for say that is this VR, VL, VC, then what you will get? So, you will see this VR is in phase with current, VL you will see this VL leads I, this means its phase is basically 90 degree phase, this VL ahead 90 degree with respect to the current, and VC lags, this lags with phase 90 degree. So, phase difference between this VL and VC basically 180 degree in opposite direction. So, you can draw basically phase diagram, and from here, so now voltage are different across the resistance, inductor and capacitance. So, this is fine resistance. So, this has also it has resistance. So, resistance is, we tell is the XL, it depends on frequency, it is a omega L, XL equal to omega L, omega is 2 pi f, f is frequency. Similarly, 1 by omega c, that is XC, omega again 2 pi f, right. So, 1 by 2 pi FC, that will be the XC, that we tell the capacitive reactance XC, inductive reactance XL, and this is resistive resistance. See. So, what will be the total resistance of this circuit? That is called impedance. That impedance one can find out impedance of this circuit. So, if you measure the VL, VR, VC as a function of current, if you vary current, then if you measure these three and if you plot them, so you will get this type of phasor diagram, you will get this type of phasor diagram. So, actually we are not going to do that one, but for calculation, if you use this phasor diagram, so then this here, so just you can modify this plot. So, here VL and VC is a 180-degree phase difference. So, basically VL minus VC you can plot, VL minus VC. So, this is in opposite direction. So, VL minus VC will be this, if so, and VR is okay as it is. Then this is a phasor diagram, vector diagram. So, this from vector addition, basically you will get if you add this plus this, so resultant one you will get this line. So, this line will be VL minus VC, this one plus VR. So, this is VR and this is VL minus VC. So, this will be vector sum, this and this. So, this will be equal to the, of course, the source voltage, and this angle between this with respect to this I, this angle is called this phase angle. Okay. So, in principle you can find out from this triangle, okay, from this triangle. So, Vs, so this is basically Vs, right, resultant on Vs. So, Vs square will be equal to the VR square plus VL minus VC whole square, right. So, VR is I into R square and VL is I XL. XL, as I told, this reactance is a resistance, inductive resistance is called reactance. So, IL minus VC IXC square. Okay. So, if total resistance in this circuit, that is called impedance, if it is Z, and current flowing in the circuit if it is I, so Vs equal to Iz, Z is impedance equivalent to resistance in the circuit. So, that will be equal to I, then from here you are getting basically I square. So, it will be I, then square root of R square plus XL minus XC whole square, right. So, comparing this, you can write that impedance is equal to square root of R square plus XL minus XC whole square. So, this is called impedance, and corresponding this phase, that is theta, will be equal to tan inverse. From here you can see tan theta equal to this by this, so VL minus VC by VR. Okay. So, from here you can get this angle theta. So, that is called phase. So, resultant whatever this you will get, so that will have phase. So, these are individual phase. It is in phase, VR is in phase, VL is leading, lagging. So, for LCR circuit, series LCR circuit, so what will be the resultant? That is basically this is the amplitude and this is the angle. So, this theta one can find out. So, if you measure VL, VC, VR, VL, VC, VR, you can find out theta. And now, do you remember this, and you can find out also impedance, right, you can find out also impedance. So, basically XL you will get, how you will get XL? If you know VL and I, so from there you will get XL. Similarly, VC and I, then you will get XC, right. So, if you measure VL, VC and VR, then you will will be able to calculate the impedance, also the phase, and this for a particular frequency, okay. So current versus voltage or voltage versus current you can study, and from there you can find out the impedance or reactance and their phase, okay. But our main interest for this experiment is to find out the resonance frequency. Now, if you vary the resonance, if you vary the frequency, then what will happen? If you vary the frequency, then this impedance changes, impedance changes, okay. Impedance changes, so your current also will change in the circuit for a particular Vs, source voltage. So at which frequency this current will be maximum, that is what our interest, and that is called the basically resonance, and that frequency is called resonance frequency. So we will find out the resonance frequency for this LCR circuit, okay. For that what we have to do, I have to measure current, as a function of frequency. Then I will plot current versus frequency, and then you will see you will get this type of curve. So at a particular frequency you will get maximum current. So that peak you have to find out, and that actually that corresponding to that peak, that you will get the frequency, and that frequency also you can calculate theoretically, because at resonance when you will get maximum current, so when this impedance will be minimum, okay. So impedance will be minimum when XL equal to XC, right, XL equal to XC. So that is the condition of resonance. So at resonance XL equal to XC, so this is omega L and this is 1 by omega C. So basically if you put 2 pi f, so f is equal to 1 by 2 pi square root of LC, okay. If you know the value of L, if you know the value of C, then you can calculate f, and experimentally you can measure f. You will find out this f from this curve I versus f frequency. So that peak value, whatever the frequency for peak value, so that will be the basically your resonance frequency. Then you can compare with this frequency. Also, yes, as I told, also for a particular frequency you can measure the impedance, and you can measure the individual reactance. So basically in this experiment I have to measure I varying the frequency f. This is main part of this experiment. Another part of the experiment is basically you measure VR, VL, VC for a particular frequency varying the current. So VL versus I, VR versus I, VC versus I, that you can plot, okay, for a particular frequency, and for that frequency what will be the XL and XC or R resistance R, that you can find out from the slope of this curve. It will be straight line from the slope of that curve. That part I will not show you here, only I will show you this resonance in this circuit, okay. So let us go to our setup. So this is the experimental setup for series LCR circuit. So this is obviously you are seeing this is L, inductor, right. This is inductor and its value is written here, it's written here 9 millihenry. So you should note down this value 9 millihenry, okay. Then this is the here is small one, that this is the basically capacitor, this capacitor. So also you can note down this value of the capacitor is written here. I think, yes, I cannot see, but anyway I will not disturb it, but it's written here. So this value is, I guess, what is the value? I think this capacitor value here we have taken, I will tell you, so that you should note down, always you should note down this value. Yes, this capacitor value 4.7 microfarad, this capacitor is 4.7 microfarad, that you should note down, and this the resistance, and this resistance is 2 ohm. Okay. So, I have inductance, so that is 9 millihenry. I have capacitance is 4.7 microfarad, and this resistance it is of 2 ohm, right. Now, I have connected them in series, you see, just check it. So, to check it, series with respect to what? Series with respect to the power supply, right. So, if you start of one end of the power supply, this is the power supply, AC power supply. Okay. Here you can vary the amplitude, as means voltage, as well as you can vary the amplitude, as well as frequency. Okay. So, that this option is there. So, AC source. So, so here, so this is the power supply, this okay, AC battery. Okay. So, so start from one electrode, then is connected to the one end of the inductor, and then other end of the inductor is connected. We have used breadboard, you know, we have used breadboard. So, it is connected with one leg of the capacitor. Okay. So, then through capacitor another leg is connected to the resistance here, and then another end of this resistance is connected to the another electrode of the power supply. Okay. So, these three are in series. So, we have to check this circuit, or you have to make yourself. I can open and just connect it, but to save time that I am not going to do it, but I showed you this connection. Okay. Now, this is AC ammeter. Okay. This AC voltmeter, yes. So, this will be used for measuring the voltage of what? Measuring the VR, VL and VC, right. So, so this actually 2 wires is coming from here. Okay. So, these the 2, you see. So, just this the voltmeter, AC voltmeter, it is giving you the RMS value VRMS. Okay. So, just if I want to measure the voltage across the resistance, then this is VR. So, I have to connect here. Okay. So, if current flows, AC current flows through the circuit, the current is same in the circuit. So, if you measure current at any point, okay, so either across this resistance, if you measure voltage across the resistance or inductance or capacitance, okay, so that voltage, the reading you will get from here. Okay. Now, I need to know the current in the circuit. So, this if I just take the voltage across the resistance, and resistance value is known to me. So, this resistance value here, this is 2, R equal to 2. So, so this whatever reading here, I will get voltage divided by VR divided by R. So, that will be the current, and this current is same for this circuit. So, this current is passing through the inductor, passing through the capacitor. So, and why we are taking this voltage across this resistance? Because this current whatever we will get from here. So, this this voltage reading will vary if I change the frequency, because that for that frequency this XL and XC that will vary, but this R will not vary. Okay. So, R all the time it is 2. So, that is why for measuring current, actually we will measure the voltage across this VR and just divide by 2, that will give me current. If I measure the voltage across this L and C, actually this XL and XC will vary with the frequency. So, all the time one has to find out the reactance XL and XC, and so that will be complicated. So, for knowing the current, we will measure the voltage across this resistance, and resistance R is known to us, is equal to 2. So, from there I will get the current. So, that is RMS value I will get. Okay. So, now let us so now if you want to measure the voltage VR, so you have to connect here, this voltmeter. Okay. Or if you want to measure the voltage across the capacitor, then these two I will connect here, okay, because this is across the capacitor, okay. And here also if you want to measure the voltage across this inductor, so this I will connect this voltmeter with this, okay. So so here you can study the variation of VL as a function of current. If you vary the current, okay, so then what will be the variation of VL, or what will be the variation of VC, or what will be the variation of VR as a function of current, that you can measure. Okay. So, that would be the one experiment that has to be done for a particular frequency. So, we will fix frequency. Here say frequency is 100 hertz. Okay. So, we will fix frequency, then I will go to the amplitude. Now, here amplitude is 5 volt. This is now, remember, this 5 volt, it is showing this peak to peak value. So, AC voltage, you know, this is the, okay. So, in positive side one peak and negative side one peak, okay. So, this peak to peak value, so that is showing this is 5 volt. So, now, but we have to take RMS value. Of course, this I do not have interest for this one, because I do not need that one, but you should know this RMS value of this one is basically this peak to peak value divided by 2 root 2. Okay. So, whatever value here, so divide by 2 root 2, that is the actually RMS value of the voltage. So, that voltage, now what I will do? I will measure VR, VC, VL. Okay. So, either you need three voltmeter, or 1 voltmeter you can use, just one after another you have to do the experiment. So, now I will vary the amplitude of this, amplitude means voltage peak to peak value, and for each voltage, so current will vary in the circuit, and corresponding voltage drop I will measure for these 3, okay. And if I measure, automatically current I will get, just whatever VR I will get. So, VR divided by these 2, that will be the current, okay. So, for a particular current I will measure VL, VC and VR. So, then I will change the voltage, Vs, source voltage, and again I will repeat the experiment. So, I can collect current versus VL, VC and VR. Now, if you plot them, VL versus I, VC versus I, then what you will get? You will get basically straight line, and from the slope you will get basically XL and XC. And frequency is known to you. I have said at 100 hertz. See, frequency is known to you. So, XL equal to omega L, 2 pi FL. Okay. So, F is known, and so from there basically you can find out L. Similarly, you can find out C. Of course, R is known to us, as I told too. So in this way you can measure the capacitance and inductance also, right. So, this part I will not show you, but my interest is show you the resonance. So, for resonance what I have to do? So, for resonance I have to measure the current. So, I will measure the voltage across this resistance, I will measure VR. If I measure VR, here I will get VR. So, I will divide by these two, it will be the current. Okay. So, now this current how current varies in this circuit with frequency, that is what I want to do experiment. So, here this is 5 volt that I will keep fixed. Now, I will go to the frequency, it's then I will start this experiment from 100 hertz frequency. So, I will note down this frequency is 100 hertz, okay, and corresponding what is the VR. So, I have to connect it with the VR here across this okay. So, I have connected in electrical circuit, always you have to see this, there should not be any loose contact. Yes, it's connected. Okay. So, I have to note that this is let me put in, okay, this is say 7 millivolt, this is 7 millivolt. So, for frequency 100 hertz. So, you have to make table this frequency versus VR and resistance is 2. So, this basically VR by R, that will be I. So, frequency versus current, that you have to make table. So, I will note down this for 100 hertz, this is 7.1 millivolt, and then I will change to 200, 110, 120. So, I will change to, now this frequency is 200, then I will take reading. Now, it is 14.7, I will note down this reading. Then I will go for 300, and then is 330. Okay. Now, it is 300, this reading is 300, that is 23.9 millivolt. Okay. So, this way I will continue 400, 500, 600. Okay. So, now I am it is 600. Okay. So, 87.3, reading is 87.3. Then I think I am close to the resonance. So, I will increase the range of the voltage. I kept it at 2 volt range. Okay. So, it is in volt range, which is 88 volt. Okay. So, then I will change, I am changing, it's a 608, 70, 680, 600. You see this now, it is increasing very fast. This current is increasing very fast. For slight change of frequency, now 720, 730, it is 200, 740 hertz, 216 millivolt, then 750, 236, 7. You see earlier with respect to 100 variation of hertz, whatever change now with respect here now with 10 variation of frequency, this change is similar. So 750, 760, 770, 780, 780, 790, you see this 810. So, it will come around 800 since I have done this experiment earlier. So, it is the near about 300, near about 290, 90, 290, 292. So, at 790 it is 290, at 780, at 780 287. So, it is decreasing. So, if I go increase it 800, it is 287 or 290 around. So, now 810 now started to decrease, 820, 820 it is now decreasing. Now I am increasing 830, 840, 860. So, it is decreasing, you know. So, peak, we saw that peak is around 800 hertz, the frequency. When it is 800 hertz, this is the maximum, it is the 292 millivolt. Then below this lower side of this frequency, it is decreasing, and higher side of the frequency it is increasing. Also, this current is decreasing. This voltage is decreasing means this is the volt. So, divide by 2, that is the current. So, this you have to take this data and then plot it, and then you will see the peak, and then corresponding what is the frequency of that peak, that is your resonance frequency. Now, in resonance condition, this XL equal to XC, that is the condition, right. So, XL are in reactance. So, I into XL is the VL, I into XC is the VC. Okay. So, XL equal to XC means VL equal to VC. So, at resonance condition VL equal to VC, it has to be. So, that I want to show you. Okay. So, let me go to the resonance condition at 800 hertz, at 800 hertz. Okay. So, this is it is a change. Earlier it was 292, but here now that is okay, it is the 280, 85, 86. Okay. We have to give time to stabilize it. So, sometimes its reading changes because of heating effect. If you pass current for longer time. So, no, it has come nicely 292. Okay. So, now this is the VR. Now, what is the VC and VL that I want to measure? So, I will disconnect from here. Let me connect here. So, okay. This is one end of the capacitor, this is the other end of the capacitor, and I want to measure. I have to go to the, what happens? So, you can see this, it is around 9 is the, it is in volt. Okay. It is coming, sorry. We should not disturb the circuit. Then it is coming around say 10 volt, 10.2 volt. Okay. So, it is in volt range. Okay. So, it is a 10.22 volt. So, this VC is 10.22 volt at resonance condition. So, now let me measure the VL, and check it. So, I want to measure VL. So, I have to connect with this Okay. But here I will feel difficulties to connect probably. Okay, let me just hold it. Let me just hold it, but it should be. It is small voltage, so it should not be problem if I hold with hand. So, you see that Vc was, but it should not. So, it is 9.22, earlier it was 10.22, it is 10.22, but I should connect properly because some resistance is coming in probably. I should, yeah, now it is a 9.34. Anyway, so 10.22 10 volt and this is 9.3 volt, 9.3 volt. So, it may not be this resonance is perfectly at this frequency. So, it can be probably 800 something, okay, 805 or 795. So, one has to tune and you have to, but I could show you properly, but unfortunately it is an no, my hand is touch here. Okay, 9.44 and 10.22 is very close. So, it has to be equal, VL and VC has to be equal. So, this difference it may be due to the just my connection, it is a loose connection, it may be for due to that, or we have to slightly adjust the frequency. It may not be 800 exactly, it may be 800, 3, 4, 5, because at the peak position this is very sensitive, this current is very sensitive. So, more or less I could show you that this VL and VC means XL is equal to XC at the resonance frequency. Okay. So, this is the experiment about the LCR. Main interest is to show the resonance, and we could show the resonance, and this resonance is frequency is around 800. So, if you plot it and then accurate frequency you can find out from the peak of this plot. So, yeah, that I was doing that one, but I do not think this I cannot open, that is the problem. This okay. So, but so if I want to show you this, okay, this is very tight, okay. So, yes, now it is 9.9, okay, 10.2 now is 9.9. So, that is what, yeah, this connection is factor, okay. So, I think this 9.9 I could show you, but only problem is you have to do proper connection, otherwise yeah, let me just leave it here. Yes, it is varying because this connection is not strong, it is a loose, there is a, so forget, but this XL is equal to XC, so VL is equal to VC. So, more or less that that I could show you, and that it will be exactly equal when you will be at exact frequency. So, one has to tune and find out. So I will stop here. Thank you for your attention.